I am Dr. R. Jyothimani, Assistant Professor, Department of Physics, Fatima College, Madurai. I would like to share some points about laser and its types. Before getting into it, we have to know some basic points about interaction of light with matter. The process of the transfer of energy from atom to light is not possible from classical point of view. However, the possibility arises if the interaction of light with medium is considered from the point of view of quantum mechanics. The transfer of energy from atom to light results in light amplification. A light amplifier can be further converted into a source of light having superior characteristics compared to traditional light source. A laser is a monochromatic coherent light source that depends on quantum process for its operation. What is meant by laser? It is nothing. It is a device that produces a very focused and powerful beam of light. The important characteristics of a laser beam is it is coherent in nature and it is monochromatic and it is highly directional. The three important processes for laser action is absorption, spontaneous emission, stimulated emission. In absorption, the atom in the ground state will be absorbed by the higher energy state when we apply the photon. In case of spontaneous emission, the atom in the excited state will reach the ground state automatically with the emission of photon without any application of photon. In case of stimulated emission, if we apply a photon on the excited state, the atom will reach the ground state by emitting more photons. The three requirements for laser action are: first one is population inversion, and the second one is metastable states, and the third one is confining radiation within the medium. The important components of lasers are active medium, pumping agent, and optical resonator. Let us see about everything. Population inversion. It's a key concept in laser physics. Normally, in a group of atoms, more electrons are in lower energy levels than in the higher ones. But in the population inversion, this situation is reversed. More atoms are in excited state than in the lower energy state. Population inversion is essential for a laser operation. In normal condition, the number of atoms in the lower energy level will be greater than the higher energy level. In case of population energy, the number of atoms will be more in higher energy level than the lower energy level. It does not happen naturally. It requires external energy input. That is called pumping, such as optical pumping, electrical discharge, and chemical reactions. The next requirement for the laser action is metastable state. This is an excited energy level of an atom where electrons stay for a relatively long time before returning to the lower energy level. It's a temporary but long-lived excited state. Normally, electrons in excited states fall back very quickly, approximately in about 10 power minus 8 to 10 power minus 8 seconds. But in metastable state, they stay much longer. This longer lifetime helps to accumulate more electrons in the higher energy level, and it creates population inversion and it enables efficient laser action. Role of metastable state in laser. Due to metastable state, electrons are pumped to the higher energy level and they quickly drop to the metastable state. They stay there longer and builds up population. This leads to stimulated emission, so we get laser light. The third requirement, that is confining radiation within the medium. Confining radiation within the medium refers to the process of trapping light inside the laser material so that it can repeatedly interact with atoms and amplify into the stronger Strong laser beam. In a laser, light is not allowed to escape immediately. Instead, it is reflected back and forth inside the medium, and this increases stimulated emission and strengthens the light. This can be done using an optical cavity, I mean the resonator. Two mirrors are placed at the ends of the laser medium. One is fully reflecting and the other one is partially reflecting. Light bounces between these mirrors many times. The common uses of lasers are the cutting, engraving, medical procedure, communication, scanning, and military and research field. Based on the materials used as active medium, the lasers can be classified into four categories like solid state laser, gas lasers, liquid lasers, semiconductor or diode lasers. There are many types of lasers like ruby laser, no-diode laser, helium neon laser, carbon dioxide laser, semiconductor laser, PN junction laser, fluorescent dye laser. The ruby laser and no-diode laser is example for solid state laser. Helium neon laser and carbon dioxide lasers are example for gas type. Semiconductor and PN junction laser is example for diode lasers. Fluorescent dye laser is example for liquid type of lasers. Let us see about the ruby laser. It belongs to the class of solid state lasers. A solid state laser is one in which the active centers are fixed in the crystal or glassy material. Solid state lasers are electrically non-conducting. They are also called doped insulator lasers. And it was the first laser. It was invented in 1960 by Theodore Maiman in USA. The ruby laser rod is a synthetic ruby crystal, aluminum oxide crystal, and doped with chromium ions at the concentration of about 0.05% by weight. Chromium ions are active centers. They have a set of three energy levels suitable for realizing lasing action. So this is the figure for ruby laser, and the next one is the energy level diagram. Let us see the construction process of the ruby laser. Ruby rod is taken in the form of cylindrical rod of about 4 cm in length and 0.5 cm in diameter. Its ends are grounded and polished such that the end faces are exactly parallel and are also perpendicular the axis of the rod. One face is silver to achieve 100% reflection, while the other is a silver to give 10% transmission and 90% reflection. The silvered faces constitute the Fabry-Perot resonator. The laser rod is surrounded by a helical photographic flash lamp filled with xenon. When the power supply is activated, the lamp produces flashes of white light. Let us see how the ruby laser is working. Ruby laser uses a three-level pumping scheme. There are two wide energy bands, E3 and E3'. Here we consider E3 and E3'. When the flash lamp is activated, the xenon discharge generates an intense white light for a few milliseconds. The chromium ions are excited to the energy bands E3 and E3'. The lifetime of this energy level is 10 power minus 9 seconds. So, chromium ions lose some energy rapidly and undergo non-radioactive transition and quickly drop to E2, that is metastable state. The lifetime of this state is 1000 times more than the E3 level. Therefore, chromium ions accumulate E2 level. When half of the chromium ion population accumulates at E2, a state of population inversion is attained between E2 and E1 level. A photon is emitted spontaneously by chromium ion that initiates a chain of stimulated emissions by other chromium ion in the metastable state. Red photos of wavelength 6943 Armstrong traveling along the axis of the ruby rod are repeatedly reflected at the end mirrors and light amplification takes place. A strong intense beam of red light emerges out of the front end mirror. Note that the green and blue components of light play the role of pumping agents and they are responsible for causing population inversion. The spontaneous photons of wavelength 6943 Armstrong corresponding to red color act as the input of the oscillator which actually gets amplified. The xenon flash lasts for the few milliseconds. However, the laser does not operate throughout this period. Its output occurs in the form of irregular pulses of microsecond duration. It is because the stimulated transitions occur faster than the rate at which population inversion is maintained in the crystal. Once stimulated transitions commence, the metastable state E2 gets depopulated very rapidly, and at the end of each small pulse, the population at E2 has fallen below the threshold value required for sustained emission of light. As a result, the lasing ceases and the laser becomes inactive. The next pulse appears after the population inversion is once again restored. This process repeats. Thank you.